Okay, good morning all, and we are going to start today from Unit 1 of your BSP 302 Thermal Physics class. Okay, so as in the syllabus, we have zeroth law of thermodynamics and first law of thermodynamics. So we will today start with zeroth law of thermodynamics. But before that, one small term or definition we need to learn, which is called thermal equilibrium. Okay, so I hope all of you have pen and notebook. So can you take notes? So I will give you notes today. So first thermal equilibrium. So can I type somewhere here? Chat box. So thermal. Okay, to everyone, thermal. So first topic is thermal equilibrium. I hope I have typed in the chat box. Maybe you can see. Okay. So so you write what is thermal equilibrium. The definition of thermal equilibrium we will learn, because once we have learned the definition of thermal equilibrium, then we can learn zeroth law of thermodynamics better. Okay. So the definition is you write down. Uh, are you writing? Please confirm me, because I am going to dictate.
Yes, sir.
Okay. Okay. So okay, you write the definition of thermal equilibrium. When all parts of a thermodynamic system when all parts of a thermodynamic system are at the same temperature, comma. So when all parts of a thermodynamic system are at the same temperature, comma, which is the same which is the same as that of the surrounding, which is the same as that of the surrounding, the system is said to be in thermal equilibrium. The system is said to be in thermal equilibrium. Okay, so I repeat the sentence. When all parts of a thermodynamic system, are at the same temperature, comma, which is the same as that of the surrounding, the system is said to be in thermal equilibrium. Okay, so that is the very easy definition of thermal equilibrium. So okay, so thermal equilibrium means all parts of a given system is at same temperature, and this temperature is also equal to the temperature of the surrounding. Okay, then the system is said to be in thermal equilibrium. Okay. Okay, so after you have learned thermal equilibrium, now we are going to learn about zeroth law of thermodynamics. Okay, so let's check what is zeroth law of thermodynamics. So for that, I would like to share one screen with you. So just give me 2 minutes, not 2 minutes, even just 1 minute. So zeroth law. Okay, just a minute. So share. Okay, I hope all of you can see this PowerPoint. So in this PowerPoint, we'll keep on adding your documents like figures or some text. So I have created this and okay, next slide. Okay, as you can see here, zeroth law, this is the figure. So can you draw this figure quickly? Just take maybe 2 minutes and draw this figure. So please draw this figure. And once you are done, so 2 minutes, once you are done, please let me know. So I will explain this figure. So the figure is there is one compartment A. Okay, compartment means system. There is another called B. There is another C. And A is at temperature TA. BES is at temperature TB, and the CES is at temperature TC. Okay. So A and B are separated by an adiabatic wall, and A and B each is separated from C by a diathermic wall. So we will discuss this figure, but first we draw it. Okay, I hope I have drawn.
Yes, sir. Yes, sir.
So can you hear my voice? Can you confirm?
Sure. Yes, sir.
Okay. Look, first I explain this briefly to you, and then I'll give you the notes. Okay, so we have a thermodynamic system A, and here we have a thermodynamic system B. Okay, so A and B are separated from one another by an adiabatic wall. What is an adiabatic? Okay, adiabatic processes, all these thermodynamic processes we will learn with time. But for now, just remember that an adiabatic wall means a wall through which no heat or thermal energy can pass. Okay, so adiabatic wall means no heat or thermal energy is allowed to pass. So heat cannot pass from A to B, or either way heat cannot pass from B to A. Okay, so that is an adiabatic wall. Now both these systems A and B are connected to another system called C, capital C, you can see here, and A and B are connected to C by a diathermic wall. Okay, so what is a diathermic wall? Diathermic wall means heat can pass through this wall. Okay, so adiabatic wall, no heat can pass. Adiabatic wall, no heat can pass. Diathermic wall, heat can pass. Okay, so Chaltha is saying that he cannot hear me. So I don't know. So all of you can hear me? Rohit, Jusra?
Yes, sir. It's audible.
Yeah, so Chaltha, maybe check your network. Okay, okay. So everyone, please check network. Okay, so the difference between diathermic wall and adiabatic wall you have understood, I hope. So adiabatic wall, no heat passes through. Diathermic wall, heat passes through. Okay. Okay. So now back to zeroth law of thermodynamics. That is the heading. You write zeroth law of thermodynamics, and let us write down the definition or what we understand by zeroth law of thermodynamics. Okay. So you write this law states that. Okay, one thing, I will upload your notes later. Maybe not today, but when I have enough notes, I will upload to Google Classroom or LMS of USTM. Sadiq is waiting in the lobby. Okay, okay. Let me check how I can allow him. Okay, my network is fine. Okay, just give me a second. Okay. Okay, so zeroth law of thermodynamics, you write down the definition of zeroth law. Okay, we are not yet at first law, zeroth law, you write. This law states that, this law states that if two systems, you write, this law states that two systems, if two systems are separately in, you write, if two systems are separately in thermal equilibrium. Look, now the concept of thermal equilibrium is coming. That's why initially I gave you the definition of thermal equilibrium. Okay, right? This law states that if two systems are separately in thermal equilibrium with a third system, if two systems are separately in thermal equilibrium with a third system, then they are also in, then they are also in then they are also in thermal equilibrium with one another. They are also in thermal equilibrium with one another. Okay, so I want to tell all the participants, all the students, that I am recording this video. Okay, so once recording is done, you can access the video. Okay, and if somebody has some technical problem or somebody is not able to hear me, but you can access the video and you can check the video. Okay, so I think that would be better. Okay, so zeroth law of thermodynamics, the statement I am repeating. This law states that if two systems are separately in thermal equilibrium with a third system, then they are also in thermal equilibrium with one another. That means in this figure, I hope all of you can see this figure. A and C are, A is in thermal equilibrium with C. Okay. Similarly, B is in thermal equilibrium with C. Okay. A equal to C. I mean, temperature of A is equal to temperature of C, and separately temperature of B is equal to temperature of C. In that case, what will happen? Temperature of A will also be equal to temperature of B. That means TA will be equal to TB, and more or less that is the main statement of zeroth law. Okay, if two systems are separately in thermal equilibrium with a third system, then they are also in thermal equilibrium with one another. Okay, I hope this is clear. You can also write in your own language. If you understand the concept, you can also write in your own language. Okay, so I think that's clear. Okay, now let us explain this particular figure which you see here in this PowerPoint presentation. Okay, so I hope all of you have drawn this figure. Okay, and anyway, I'll share the note on the this thing also with the video. No, I'm recording the video. Okay, so you write down. Consider three systems A, B, C. So you can see in the figure, it is very clear. We have three systems A, B, C. Consider three systems A, B, C at temperatures you can see their temperatures TA, TB and TC respectively. So A is a temperature TA, B is a temperature TB and C is a temperature TC respectively. Okay, the system A and B are separated from each other. The systems A and B are separated from each other by an adiabatic wall. As you can see, A and B are separated from each other by an adiabatic wall. Just give me a moment.
Hello, hello.
Okay, so systems A and B are separated from each other by an adiabatic wall. So comma, you write the definition of adiabatic wall. So of course we will learn with time, but for now, so a wall, adiabatic wall, comma, a wall which conducts no thermal energy. That is the definition of an adiabatic wall. A wall that conducts no thermal energy. No thermal energy. So then both the systems A and B, you can always refer to the figure. The figure is in front of you. Both the systems A and B are in contact. Both the systems A and B are in contact with a third system. Both the systems A and B are in contact with a third system C. C, A, boy C, A is in contact with C, B is in contact with C, with a third system C through a diathermic wall. So diathermic wall you can see here, through a diathermic wall, comma. So what is a diathermic wall? So just let us write down. So comma, a wall which allows heat to pass through. A wall which allows heat to pass through. That is the definition of a diathermic wall. A wall which allows heat to pass through. Okay. So now we have to understand a little bit conceptually. So let us try to understand. Okay, so look, okay, forget between A and B. Let us discuss what is going on between A and C or B and C. So we said that A is in contact with C through a diathermic wall, and a diathermic wall means a wall through which heat can pass. What does that mean? That means heat will pass from A to C until their temperatures are equal. Okay. So, okay, let me give an example. You have a very hot piece of iron or any metal. You bring that in air. You keep that in air. A hot piece of iron you have heated in fire, and then you keep it in air, no, just to cool it down. So what happens exactly? So heat flows from the hot iron piece to the air, or heat flows from the air to the iron piece. So what happens exactly? Can anyone answer?
Sir, heat flows from the hot iron to the air.
Yeah, exactly. So heat flows from the hot body to the cold body. Okay, more or less this is related to the second law of thermodynamics, which we will learn with time. Okay, so in this case, what is going on? A and C are at different temperature. Look, iron and air, they are at different temperatures. Okay, and therefore heat flows from iron to the air. That means after some time, after maybe 10 15 minutes, 20 minutes, 30 minutes, both the iron piece and the air will be at the same temperature. Okay, because the hot iron has left all its heat to the air. Okay, similarly here A and C are connected by a diathermic wall. That means this wall conducts heat, or heat can pass through this wall. Okay, so after some time what will happen? A and C will get same temperature. That means Ta will become equal to Tc. Why? Because heat flows from A to C. If we consider that A is at a higher temperature than C. So anyway, so the thing is that if you keep two bodies in contact, suppose my two hands, they are in contact. One is suppose at a higher temperature, the other one is at lower temperature. Then what will happen? So after some time, you will see that both hands are equally, uh, they have equally hot, or their temperatures are same. Okay. That is also the case here. So heat will flow from A to C and both will get the same temperature. That means Ta becomes equal to Tc. That means what? A and C are in thermal equilibrium now. And we have just learned the definition of thermal equilibrium. The definition of thermal equilibrium is that the temperatures of two bodies, or the temperature of one body, is equal to that of its surrounding. Okay. Okay, so you write down. I hope you have understood. Okay, so heat flows from one body to another and they reach the state of thermal equilibrium or same temperature. You write down. Thus, the systems A and B, next you write, thus the systems A and B are individually, thus the systems A and B are individually in equilibrium. Thus the systems A and B are individually in equilibrium with the system C. Thus, okay, I repeat, thus the systems A and B are individually in equilibrium with the system C. So same is the case with B and C, the thermic wall. Heat flows from B to C and they get the same temperature. Okay, that is the definition of our thermal equilibrium we have just learned at the beginning of this class. Okay, next you write next paragraph. Since systems A and C are in thermal equilibrium, since the systems A, capital A and capital C are in thermal equilibrium, the temperature of the system capital A and C are in thermal equilibrium. Therefore, the temperature of the system A, which is capital, so the temperature of the system A must be equal to the temperature of the system C. The temperature of the system A must be equal to the temperature of the system C. Therefore, or so, whatever you write, so TA equal to Tc. So TA, this temperature you can see, this temperature is equal to this temperature. So TA is equal to Tc. Okay. Okay, suppose this is equation number 1. So TA is equal to Tc is equation number 1. Okay. Now again, what about B and C? Same thing we have to write. Since the systems B and C since the systems B and C are in thermal equilibrium, the temperature of the system B, since systems B and C are in thermal equilibrium, the temperature of the system B must be equal to the temperature must be equal to the temperature of the system C. Must be equal to the temperature of the system C. So now B and C are in thermal equilibrium, so B's temperature is equal to C's temperature. That means TB. So you write TB is equal to TC. So TB is equal to TC. And suppose this is equation number 2. So TA equal to TC was equation number 1. And here we have TB equal to TC is equation number 2. Okay. Okay, now you see, you compare, if I ask you to compare equations 1 and 2, what do we get? We get, you check in your notebook, TA is equal to TC and TB. What do we get?
T equal to TB.
TB.
Yeah, exactly. TA is equal to TB. Right. So you write comparing equations 1 and 2. Comparing equations 1 and 2, we have TA equal to TB. Comparing equations 1 and 2, we have TA equal to TB. That means this temperature TA is equal to this temperature. Oh, suppose this is equation 3. Okay. Okay, so equation 3 is Ta equal to Tb. So what does this equation 3 mean? You write equation 3 shows that the systems A and B, equation 3 shows that the systems A and B are also in thermal equilibrium. A and B are also in thermal equilibrium with each other. A and B are also in thermal equilibrium with each other. Okay, so have you understood this is basically this diagram. So I am quickly explaining again to those which if I came late or something. So A and B are two thermodynamic systems. They are separated by an adiabatic wall. But A and B are also like no. There is also another system C, which is connected to A and B individually through a diathermic wall. So adiabatic wall means no heat can pass through this wall, and diathermic wall means heat can pass through this wall. So now since heat can pass through A and C, therefore what is going on? After a while, A and C will get thermal equilibrium. Thermal equilibrium means what? A's temperature becomes equal to C's temperature. So Ta is equal to Tc. That is equation 1. Now separately, the temperature of B will be equal to temperature of C. Why? Because heat will pass through this diathermic wall between these two thermodynamic systems B and C. Okay? That means equation 2 is Tb equal to Tc. So finally, what we are getting, since Ta equal to Tc and Tb equal to Tc, therefore Ta will equal to Tb. So Ta and Tb will be at thermal equilibrium, although there is an adiabatic wall separating them. It doesn't matter, heat does not pass through the adiabatic wall, so it doesn't matter. But since there is the third system C, due to this third system C, so all these three thermodynamic systems Ta, Tb and Tc, Ta, Tb and Tc will be at the same temperature, or they will achieve thermal equilibrium. So basically this is the zeroth law of thermodynamics. Okay.
Thermodynamics.
Yeah. Oh, I can hear my own voice maybe. Okay, so quickly let us go to another small topic: significance and concept of temperature. You write down quickly: significance and concept of temperature. Significance and concept of temperature. Also, what is temperature? So already we have learned what is temperature. Who can answer me? Just at the beginning of the class, we learned what is temperature.
The degree of hotness or coldness
The
to
degree
be
of
measured.
hotness and coldness. Okay, but this is we did not learn this definition exactly. Of course, this is one way to define temperature. But earlier this class, uh, whoever was there, I think Sadiq came a bit late, but those who have been here from the beginning, Dansurang was there, then Jusrang was also there, Rohit was also there. So you learned thermal equilibrium. So what does thermal equilibrium say? Thermal equilibrium says that
Uh,
two bodies are at same temperature.
when two bodies are at same temperature.
Yeah, exactly. So Dansurang is speaking. Very good. Two bodies are at same temperature. That is thermal equilibrium. That means temperature is a quantity, or temperature is a factor which determines whether one system is in thermal equilibrium with another system or not. If we say that A and B are in thermal equilibrium, what does that mean? Temperature of A must be equal to temperature of
A
B.
must be equal to B.
Yeah, exactly. And if they are not in thermal equilibrium, then what do you understand? Temperature of
Temperature of A not is equal to temperature of B.
is not equal to B. Very good. Temperature of A
Well,
is
it's
not
not equal.
equal to B. Yeah. So temperature is determining whether one system is in thermal equilibrium with another system or not. So this temperature quantity is determining, okay? So from that concept of thermal equilibrium, what I mean to say is from that concept of thermal equilibrium also, we can define temperature. Okay, so if we have understood this, let us write down significance and concept of temperature. So yeah. So okay, so one request to all of you. So you follow the courses, whatever you are learning, thermal physics or electronics or mathematical physics. You start from the beginning, okay? Like whenever classes are being taken, so that you don't have problem before examination. Okay, so clear your concept. That way it will be easy for you to catch up later also. Okay, so you still have 4 semesters, so yeah, so that way you can like it's better for you. Okay, okay, so you write the significance of zeroth law of thermodynamics. The significance of zeroth law of thermodynamics lies in the fact that the significance of zeroth law of thermodynamics lies in the fact that lies in the fact that two systems in thermal equilibrium lies in the fact that two systems in thermal equilibrium must have a two systems in thermal equilibrium must have a common characteristic must have a common characteristic. And what is that characteristic? That characteristic is nothing but temperature. Common characteristic called temperature. Okay, so two systems in thermal equilibrium must have a common characteristic temperature. So it doesn't matter if one thing is bigger than the other or smaller than the other. If one has like I don't know, one is a different thing, the other one is another thing. It doesn't matter. So thermal equilibrium means they must maintain equal temperature. The temperature of both the bodies must be equal. Okay, and temperature is the quantity which determines whether two systems are in thermal equilibrium or not. Okay, so this is one definition of temperature. Okay, okay, so you write the definition. So hence temperature of a system, you write hence.
Sir, can you repeat the last statement? What you said about temperature? I didn't hear that.
So
The last statement.
yeah, the significance of zeroth law of thermodynamics lies in the fact that the two systems are
No, no, sir. No, not that part.
which one?
Sir, you said something on temperature. Something you said with the last statement. When the voice was cracking, so I could not hear the last statement.
Oh, maybe
You say something.
so temperature is the only quantity which determines thermal equilibrium, right? So it doesn't matter. Maybe one body is larger than the other one. So they may have different physical characteristics or other chemical characteristics, whatever. But only one quantity determines if they are in thermal equilibrium or not, and that quantity is temperature. So apart from temperature, no other quantity, like no other physical characteristic can determine if two bodies are in thermal equilibrium or not. So when we are specifically talking about thermal equilibrium, so only common parameter is temperature. Okay, so that is what I was talking about. So temperature is the only quantity which determines thermal equilibrium irrespective of physical characteristics of the bodies or of the objects concerned. Okay, so you write down the definition of temperature. So hence temperature of a system is defined as the property. Hence temperature of a system is defined as the property which determines whether or not a system is in thermal equilibrium with another system. So once again I am repeating, hence temperature of a system is defined as the property. Hence temperature of a system is defined as the property which determines whether or not a system is in thermal equilibrium with another system. Okay, so I hope this is clear now. And yeah, so we have learned today what we have learned. We have learned about the concept of thermal equilibrium. We have learned about Zeroth Law of Thermodynamics, and we have also learned about the definition of temperature, or how you will define temperature. So all the things are related to one common thing. So it's, that is thermal equilibrium. Okay, thermal equilibrium means, in short, they are at same temperature. Zeroth law means, like, if two bodies are in thermal equilibrium with another body, then those two bodies are also themselves in thermal equilibrium. And significance of or the concept of temperature, in significance and concept of temperature. So it is the temperature which determines whether two systems are in thermal equilibrium with one another or not. So that's what we have learned today. Okay. Okay, so I think today, okay, so this meeting, I got the message, meeting will end in 5 minutes. So in 5 minutes it will end. Before that, quickly I want to show you the first law of thermodynamics, which also I showed to you in the last class. So next day we will start with the first law of thermodynamics. Okay, and this note I will upload in Google Classroom. I have made separately. And also I'll try to upload it to LMS of USTM, but USTM LMS was not working. No, I could not log in. There was some problem. I could not log in. So, I will see. I will contact the person concerned.
Sir, sir, you will upload the same note, sir, you will, or some other thing note you will upload?
No, same note I will upload. Same note, because
Okay, sir.
this thing you can access in future also. No, because in Google Classroom, that is not today maybe, but I will add first law of thermodynamics note and then upload, because today I think most of you have taken the notes. So yeah, so not today, maybe after another class, both 2 days class notes I will upload. Okay. Okay, so let's move to in 2-3 minutes we don't have much time. So let's first law of thermodynamics we actually discussed in the last class. You can see. So, okay, I've come to full screen mode. So, the change in internal energy of a system is equal to the change in internal energy of a system delta U, which we have learned what is delta U, is equal to heat added minus the work done by the system. So, if you supply heat, or in other words, okay, I'll give you the notes with proper definition, etc. In other words, if you supply heat to a system, which is the Q, then one part of this heat is used up in doing this in changing internal energy, and the other part is used up in doing work by the system. Okay, so can I write here something? Let me just try. Let me see what this is. Yeah, I think I can write something. So Q is equal to, I'm trying to delta U plus, same thing, Q is heat supplied, delta U is increase in internal energy, and W is the work done by the system. Okay, so this is basically the first law. If you supply heat to a system, one part of it goes to increase internal energy and other by work done. So internal energy is the total energy or content within the system, be it like potential energy and kinetic energy of the atoms and molecules of the system, and the work done by the system. And work done by the system is mainly dependent on your this thing, what is that called, volume. Work done is also dependent on volume. So I think with this we come to an end, and we will see in the next class. Okay, and the video, if possible, I will try to share with you. Okay, so thank you all,
Thank
and see
you,
you
sir.
in the next class. Okay.
Thank you so much.
Okay, so take care and see you in the next class. So I'm stopping the share. Yeah, we are at the main screen, and yeah, so thank you. We'll see you in the next class.